Hello, today we'll talk about non-homogeneous second-order differential equations. In particular, we'll discuss the method of undetermined coefficients. So, what is a non-homogeneous linear differential equation? Well, any equation of the form y double prime ay prime plus by equals r of x is called a non-homogeneous differential equation. So non-homogeneous basically means that on the right-hand side of the differential equation, you don't have a zero, you have some function. So given such equation, so this is non-homogeneous given such equation, the solution consists of two parts. So the solution y consists of the homogeneous solution plus the particular solution. The homogeneous solution comes from solving the original differential equation in the homogeneous condition. So to get the homogeneous solution, we have to solve the equation y double prime plus ay prime plus by equals 0. So we basically copy the original equation, but instead of r of x, we put 0 on the right-hand side. And the solution of this homogeneous equation is called yh. To get the second part of our general solution, yp, we have to look at r of x. So we have a table that tells us how to find yp. And yp, as I said, depends on rx. So the first case is if r of x is an exponential function e to the lambda x. In that case, we choose the particular solution to be c times e to the lambda x. So wherever the lambda is for r, we choose the same lambda for yp. And c is a coefficient that we will have to find. If r of x is a polynomial of degree n, then yp is also going to be a polynomial of degree n. So let's write it as an x to the n plus an minus 1 x to the n minus 1 ax plus a0. So this is the general polynomial of degree n with coefficients an minus 1, a1, a0. And our job is to find those undetermined coefficients. And the third case is if we have either sine omega x or cosine omega x. In this case, the solution is going to be a cosine omega x plus b sine omega x. So if you just have sine omega x, this will be y of p. Or if you have cosine omega x, this will still be y of p. Okay? So now let's do a few examples to demonstrate how this method works. So here's an example of a non-homogeneous second-degree equation. Why don't you take a second and see if you can solve it on your own. All right, let's try it together. So first, let's find the homogeneous solution. To find the homogeneous solution, we take the original equation and just put a 0 on the right-hand side. All right, so we all know how to do this equation because it's a second-degree equation with constant coefficients. We have to solve the characteristic equation. So that would be lambda squared minus lambda minus 2 equals 0. This is a quadratic equation. I can factor it, lambda minus 2, lambda plus 1. So we get two solutions, lambda 1 equals 2, lambda 2 equals minus 1. So I have two real solutions. That means y of h is c1 e to the power 2x plus c2 e to the power minus x. So that's our homogeneous solution. Next, we have to find the particular solution. Well, the particular solution depends on r of x. So if you look at the table, it tells you that if r of x is the exponential function, then yp also has to be the same exponential function. Okay. So this comes from the table. Now, our job is to find what is the value of c. Now, the idea is that this y of p is supposed to be the solution of the differential equation. So if we plug it into the differential equation, the left-hand side has to be equal to the right-hand side. So let's do that. We need to know what's y prime. So y prime will be 3c e to the 3x, and y double prime would be 9c e to the 3x. So if I take these terms and plug them into the left-hand side of the equation, I'll get 9c e to the 3x minus 3c e to the 3x minus 2 times y, c e to the 3x. So that's the left-hand side of the differential equation. And this must be equal to whatever we have on the right-hand side, which is e to the 3x. Now, if I combine the terms on the left-hand side, I'll have 9c minus 3c minus 2c. So that gives me 4c e to the 3x. And on the right-hand side, I still have e to the 3x. Well, so if I cancel e to the 3x, that means that 4c has to be equal to 1. So that implies that c is equal to 1 over 4. So we get our solution, the general solution. Remember, it was y of h. So y of h we found is c e to the 2x plus c2 e to the minus x plus y of p. And y of p is this, and c here is 1 over 4. So that's our y of p. Y of h plus y of p. That's our solution. Now let's figure out c1 and c2 using the initial value conditions. We need to know what is y prime. So let's take the derivative. And if we take the derivative, we get 2c1 e to the 2x minus c2 e to the minus x plus 3 over 4 e to the 3x. All right. Now the first condition says that if I replace x with 0, y will be equal to 2. So taking this, y equals 2. If I replace x with 0, I get c1 plus c2 plus 1 over 4. And the second condition says that if I replace x with 0, y prime will be equal to 3. So I get 3 equals, let's put 0, get 2c1 minus c2 plus 3 over 4. So I have a system of equations, two unknowns. We solve the system of equations and we get our answer. So that's just algebra, and I hope you can do it. I'll just give you the final answer. So c1, I guess in my notes I start with c2. c2 is 5 over 12. And c1 is 7 over 4 minus 5 over 12. So this is going to be, if I multiply by 3, be 21 minus 5. So that's 16 over 12. Okay? So we found c1 and we found c2. you plug them into the general solution, and you're done. Okay. So here's another example of a second order non-homogeneous differential equation. Why don't you take a second, see if you can solve it on your own. Okay, let's try it together. So first step, start from the homogeneous solution. We take the original equation, y double prime plus 5y prime plus 6y, and just put a 0 on the right-hand side. Again, this is a second-order equation with constant coefficients. We solve it by solving the characteristic equation, lambda squared plus 5 lambda plus 6 equals 0. I can factor this, lambda plus 2, lambda plus 3. So we get 2 roots, lambda 1 equals negative 2, lambda 2 equals negative 3. So our solution, YH, is C1 e to the negative 2x, C2 e to the negative 3x. All right, so we found the homogeneous solution. Now let's find the particular solution. So remember, the particular solution depends on the function r of x. Here the function r of x is first degree polynomial. So yp also has to be a first degree polynomial. We'll call it ax plus b. And our job is to find what is a and what is b. So the idea again is the same as in the previous example. Y of p must satisfy this differential equation. So if I take the derivatives and put them on the left-hand side, that has to be equal to the right-hand side. So let's take the derivatives. Y prime is a, and y double prime would be 0. Let's plug these into the left-hand side of the differential equation. So y double prime will be 0. We don't have to write that. And then I'll have 5 times y prime, which is a, plus 6 times y, which is ax plus b. And that must be equal to the right-hand side, 2x plus 3. Now, the next thing you have to understand is that in order for the two sides to be equal to each other, the coefficients of x on the left have to be equal to the coefficients of x on the right. And the constants on the left have to be equal to the constants on the right. So let's see, what's the coefficient of x on the left-hand side? Well, if I multiply by 6, I'll have 6ax. So that's the only term with x on the left-hand side, and its coefficient is 6a. And 6a has to be equal to the coefficient of x on the right-hand side, which is 2. So that means a is 1 over 3. Next, let's take the constants. So on the left-hand side, the constants are 5a and also 6b. 5a plus 6b. And that has to be equal to the constants on the right-hand side, 3. All right? Well, we already found a. A is 1 over 3. So what I have is 5 over 3 plus 6b equals 3. So from here we can solve for b. If I move 5 over 3 to the other side, it will be, I guess, 4 over 3. And if we divide by 6, 18. Oh, maybe you can write it as 2 over 9. And let me just double check. Yep. That looks right. So we found that a must be equal to 1 over 3. And b must be equal to 2 over 9. So now we're ready to write our general solution. Remember, the general solution was y of h plus y of p. Here's y of h, c1 e to the negative 2x, c2 e to the negative 3x, plus y of p. Here's y of p, 1 over 3x plus 2 over 9. Okay. Next, we have to find C1 and C2 using the initial value conditions. Let's find y prime. So y prime would be negative 2c1 e to the negative 2x, negative 3c2 e to the negative 3x. And if I take the derivative here, I just get 1 over 3. All right. So this term says that if I replace x with 0, y would be 3. So replace y with 3, x with 0. So put 0 here, put 0 here, and put 0 here. And we'll get c1 plus c2 plus 2 over 9. And for the second line, if I replace x with 0, y prime has to be equal to 2. So if I replace 0 here, I'll get negative 2c1, negative 3c2, plus 1 over 3. Again, we end up with 2 equations and 2 unknowns. And I'm sure you all know how to solve it. And I'll just give you the answer. So if I solve these 2 equations, I get c1 equals 10, and c2 equals negative 65 over 9. Okay? So then we take c1 and plug it in here, and take c2 and plug it in here, and you're done. Okay? Here's another example. Why don't you guys take a second, see if you can solve it on your own. All right, let's try it together. So as usual, first step is to find the homogeneous solution. For that, we copy the original equation and put 0 on the right-hand side. To solve this, we have to look at the characteristic equation, lambda squared. Now notice there's no y prime here, therefore there will be no lambda here. And we just then put negative 4. So solve this equation, we get lambda 1 equals 2, lambda 2 equals negative 2. So our solution is going to be yh is c1 e to the 2x, c2 e to the negative 2x. Then the second step is to find a particular solution. The particular solution has to be the same as r of x. So here r of x is e to the 2x. So yp is also going to be e to the 2x with a constant. But now notice something strange happens. E to the x is already contained in the homogeneous solution. So we can't use it. What we have to do in this case is multiply yp by x. Okay? So this is kind of a new rule. If your first candidate for the particular solution is already contained, see, this e to the 2x is already contained in the homogeneous solution, then you have to multiply your solution yp by x. Right. So now we're going to take the derivative of yp and you put it on the left-hand side, make it equal to the right-hand side. If I take the first derivative, what do I get? Well, let's see. To take the derivative, I have e to the 2x times x. So I have to use the product rule for the derivative. And I get 2 e to the 2x times x plus e to the 2x, and the derivative of x is 1. Okay? And to take the second derivative, let's see, here I have to use product rule again. So by the product rule I'll get 4 e to the 2x x plus 2 e to the 2x, and then this guy will give me 2 e to the 2x. So let's plug y double prime into the differential equation, and we'll get c times 4 e to the 2x x plus, this gives us 4 e to the 2x, So this is y double prime, and then it goes minus 4 times y, and this is our y, c e to the 2x times x. All right, so that's the left-hand side of the differential equation, which must be equal to the right-hand side, 3e to the 2x. All right. So on the right-hand side, we have 3e to the 2x. And what must be true is that in order for the left-hand side to be equal to the right-hand side, the coefficient of e to the 2x on the left-hand side must be equal to the coefficient of e to the 2x on the right-hand side. So what's the coefficient of e to the 2x here? Well, let's see. I have e to the 2x here, and that's it. All the other ones, this term and this term, they contain x in it. So we're not going to consider them. The only term we're going to consider is this one, because it's the only one that's just e to the 2x. So on the left-hand side, we have c times 4e to the 2x. So the coefficient that I have to consider is 4 times c. That's the coefficient on the left-hand side of e to the 2x. And on the right-hand side, the coefficient of e to the 2x is equal to 3. So from there, it follows that c must be equal to 3 over 4. Okay? So you've seen that we use this idea over and over again, that when you have an equation, in order for the equation to be true, the coefficients of the terms on the left-hand side have to be equal to the coefficients of terms on the right-hand side. And from there, you get certain equations that help you to find what are the constants. Okay? So here's another differential equation. Why don't you take a second and see if you can solve it on your own. All right, let's try it together. So again, the first step is to find a homogeneous solution. So we take the original differential equation and set the right-hand side equal to 0. We have to look at the characteristic equation, lambda squared plus 4 equals 0. So this equation has two solutions, plus minus 2i. So these are complex solutions. Alpha, the real part of this complex number, is 0, and beta is 2. So if you remember, this is case 3, and the solution is going to be e to the alpha x, alpha is 0, times c1 cosine beta x plus c2 sine beta x. Well, e to the power 0 is 1, so we don't have to write it, and we just get c1 cosine 2x plus c2 sine 2x. That's our homogeneous solution. Next, we have to look at the particular solution. For that, we're going to look at the Rx. Now notice Rx is sine 2x. And from the table, that meant that we have to choose our solution to be a cosine 2x plus b sine 2x. Okay? Combination of cos 2x and sine 2x. So if I have sine 2x by itself, I still have to take both cosine and sine in yp. Even if I had, let's say, cosine 2x here, I would still choose yp to be cos 2x plus sine 2x. All right, so let's see. Again, we have to be careful because the particular solution, cos 2x and sine 2x, is already contained in the homogeneous solution. So in my homogeneous solution, I also have cos 2x and sine 2x. So remember, in that case, what we have to do is multiply our solution by x. All right, so we'll take this as our yp. Now the rest is the same. We want to take the derivatives and put it on the left-hand side of the differential equation, make it equal to the right-hand side. So Let's do that. Y prime would be, I'll be using the product rule. So take the derivative of this part. And that would be minus 2a sine 2x plus 2b cosine 2x times x plus a cos 2x plus b sine 2x. So that's our derivative. And then we have to take the second derivative. Again, for this term, I have to use the product rule. And by the product rule, we'll get negative 4a cos 2x, negative 4b sine 2x, plus, times x, plus negative 2a sine 2x, plus 2b cos 2x. So this is the derivative of the first term using the product rule. And then the derivative of the second term is going to be negative 2a sine 2x plus 2b cosine 2x. Okay. So we have the second derivative, and we're ready to plug it into the differential equation. Let's think for a second if there's anything that can be canceled out, and it doesn't seem like that. Right. Well, instead of copying y double prime, which is a very long expression, and putting it in here and then multiplying by 4 times y prime, let's just think about it from a distance. So what we'll do is, I have to do is take the second derivative, plug it in here, and then do plus 4 times the original function, right? I'll do that. And then I know that that has to be equal to the right-hand side. And remember what we said is, in order for the left-hand side to be equal to the right-hand side, the coefficients of the similar terms have to be equal to each other. The coefficients have to be equal. Well, on the right-hand side, I have sine 2x, and its coefficient is negative 12, right? Coefficient of sine 2x is negative 12. Let me actually write it this way. So let's think about the term sine 2x. The coefficient of sine 2x on the right-hand side is negative 12. Okay? And that has to be equal to the coefficient of sine 2x on the left-hand side. And what would be the coefficient of sine 2x on the left-hand side? Well, I have y double prime. So here's y double prime. And let's see. In y double prime, I have 2 terms with sine 2x. Right? This is sine 2x, and this is sine 2x. And what is their combined coefficients? Well, this part gives me negative 2a, and this part also gives me negative 2a. So I get negative 4a. That's the coefficient from y double prime. And I also have to do plus 4y. But in y, there is no sine 2x, because this sine 2x gets multiplied by x. So here I have no sine 2x. Therefore, this term doesn't contribute anything. So all I get is negative 12 equals negative 4a. So that means that a has to be equal to 3. Now let's do the same thing for cosine 2x. What's the coefficient of cosine 2x on the right-hand side? Well, there is no cosine 2x, so its coefficient is 0. Okay? And what's the coefficient of cos 2x on the left-hand side? Well, cos 2x will come from y double prime and y, right? So if I look at y double prime, here it is. I have 2 places with cos 2x. This is one place, and this is another place. And the coefficient here is 2b, and the coefficient here is also 2b. So that gives me 4b. Okay. Now I also have to look at 4y. But if I look at y, there is no cos 2x. This cos 2x gets multiplied by x. So this term is really, so let me actually write, maybe I should write it down. If I multiply by x, I get ax cos 2x plus bx sine 2x. So this coefficient is not cos 2x. This coefficient is x cos 2x. So I'm not going to consider it. I just need pure cos 2x. And there is no pure cos 2x for y. So this guy doesn't give me any cos 2x terms. I only get them from y double prime, which was 4b. So I have 0, the coefficient of cos 2x on the right-hand side, equals 4b. So that means b is equal to 0. So what is our particular solution? Well, here's the particular solution. And we just said that a will have to be equal to 3 and b will have to be equal to 0. So we'll get 3x cos 2x. That's our particular solution. And our final answer, let's write it here, will be the homogeneous solution, c1 cos 2x plus c2 sine 2x. That's the homogeneous solution. Plus the particular solution, 3x cos 2x. All right. We are done.